I'm very pleased that Doug Keszler could join us here tonight. I've been aware of his work since I came to OSU back about 2005. He was involved in the development of transparent transistors technology that's being used in commercial production today. He came to OSU in 1985, 1986, doing a postdoc at Cornell. Before that, had done his PhD at Northwestern. He's won a number of awards for his teaching and his research at OSU. He was an OSU Researcher of the Year in 2003, and today he is the director of the Center for Sustainable Materials Chemistry, which is a unit that, not a unit, it's an enterprise. It's a collaboration between Oregon State, University of Oregon, with universities like Davis, Washington University, and St. Louis, Rutgers, federal labs, companies. This is a major undertaking funded by the National Science Foundation to jumpstart the fundamental chemistry behind the electronics and the materials that we take for granted in our everyday lives. And Doug's going to tell you how this is going to be a solution for some major problems we're facing environmentally. So please give Doug a nice welcome for Science Talk.
Okay, it's great to see a big crowd here. I think you're all really here to generate some energy and keep us all warm on this cool evening. I'm going to sort of take a random walk and try to connect what we're doing with some water-based chemistry, some cutting-edge electronics, okay, and then look at the energy problem in the context of climate change, and hopefully have an uplifting message from this. No doom and gloom tonight. We're about solutions. So what I'll do is primarily talk a little bit about what we're doing in the center that Nick mentioned around really some chemistry solutions. But I'm also a member of a similar center being funded by the Department of Energy, the Center for Inverse Design, and there's a nice interplays between these two centers that really allow us to bring things together that we really couldn't do if we didn't have these centers working a little bit together at least. Okay, so I spend a lot of my time during the day thinking about these three topics: simplicity, sustainability, and innovation. I think if you look at most academic researchers, they actually do the opposite of this. They like to look at really complex problems, dig in deep, and look at all this complexity. I think I have attention deficit syndrome, and I'm not smart enough to work on really complex problems. So we like to keep things really simple. Again, the other aspect of that is that, if you look at most of the things we use in society, they really tend to be things that are easy to make. They're made from very simple building blocks. So that's really what we try to do, is come up with these simple building blocks, okay, that we can transfer to actual use, things that you would like to use. Okay, but we're all products of our environment. I've been living here in Oregon and Corvallis for 28 years now. Okay, heavily influenced, around these aspects of sustainability. So when we're doing things, thinking about simplicity, turning it into some innovation, we want to do that in a very sustainable way, okay, a very environmentally conscious way, so that we don't create problems with what we're trying to do. Okay, so part of the talk here is about the grandest chemistry experiment that's ever been undertaken by man. Okay, so I think we all know what this experiment is. We're all participants in this experiment. So it's the experiment of the planet. We're basically inverting the planet. We're taking oil from under the ground, and we're bringing it up to the surface, and we're turning it into carbon dioxide. Okay, so we know during the past 100 years that that's contributed to increasing the temperature of the planet by that only 1 degree. I think we're starting to see the consequences of that. Okay, and if you look at the predictions out of the Intergovernmental Panel on Climate Change, there's many different scenarios with respect to what's going to happen with the CO2 concentration over the next century or so. Okay, so we're on this upper line here, a substantial increase in CO2 by 2100. Okay, and just to give you a magnitude of what's going on here, if you look at the average CO2 concentration, over the past 600,000 years, okay, we're already above that average, okay, and growing, very rapidly, okay, in terms of the concentration of CO2. Okay, so, before the Kyoto Protocol in '99 or so, our increase in CO2 was going out about 1% per year, okay, and since the Kyoto Protocol, what's happened? Anything? It's actually gone from 1% to 3%. Okay, so past 10 years, we're actually growing much faster than before Kyoto, so we're on this line here. Okay, and that line by 2100 is going to give us, better than a 10-degree increase in temperature. Again, even on the low line here, we're looking at a couple of degrees increase in temperature. Okay, and I'm not going to be around in 2100. Some folks in the room might, but these kinds of increases are going to be devastating. Okay, with respect to what's going to happen in the world. Okay, but through digging up all these fossil fuels and using them, we've actually done some pretty good things. You look at the human lifespan over the past 100 years, our wealth. Okay, look at the cost of food, what we're actually paying for energy, okay, and what technology has done for us in terms of communications. We have used this energy to do a lot of good things. Okay, and what we like to concentrate on is what's happened here with the cost of communications, representing what's been happening in technology. Okay, where if we look at computing power over the past 100 years, we've had this near exponential growth. Okay, in terms of what's been happening in terms of what our smartphone capabilities are, PC capabilities. Okay, and this is the area that I operate in, the people I work with operate in, and we think this is really the solution to the global climate crisis. If we can get on this type of a growth curve, okay, in terms of offering solutions to global climate change. This is one way that we can very quickly, okay, address the situation and do it at a cost, okay, that we're all comfortable with and will allow us to eventually just simply replace fossil fuels, okay, with more sustainable energy sources. Okay, so the ultimate goal here is really to move away from fossil fuels so that we have zero carbon dioxide emissions. Okay, let's just look at the magnitude of the problem. The world right now consumes this big amount of energy, 16 terawatts, 16 trillion watts, which probably doesn't have much meaning to anybody. It's just a big number. About 80% of that comes from fossil fuels, so producing CO2, okay, 5% nuclear, okay, 15% renewables by far and away. The majority of that is coming off the dams, places like the Columbia River up here. Okay, so we can go on as we are with fossil fuels, generate CO2. One of the solutions that's been proposed then, at least around power plants, okay, is just to push that CO2 back underground, into, maybe aquifers, which doesn't sound like a good idea because we like to use water. You could go into a depleted oil gas reservoir, go deep ocean. Okay, a lot of technical issues with this. Even a 1% leakage of the CO2, okay, if you could even pump it down there in the first place, okay, would over a period of decades, you just have all the CO2 coming back up. Okay, places like Texas, I was reading the other day, they've actually drilled nearly 1.5 million holes, okay, into the ground in Texas looking for oil. Okay, so that gives you a lot of places for the CO2, okay, just to leak back up into the atmosphere. Okay, so I think there's a lot of science and engineering going on, seeing if we can make this work. But if I were making investments, I wouldn't be putting my money here, okay, as this is a solution to the CO2 problem. Okay, the other approach to this is to go nuclear. This is pretty popular here in Corvallis with a company like NuScale, trying to come up with really small modular nuclear power plants. Okay, but if we look at the size of the problem, a typical nuclear power plant might get you 1 billion watts. We need 16 trillion watts. Okay, so to get there, we need more than 10,000 nuclear power plants. Okay, we'd like to have these built very quickly, okay, so we can knock out the CO2. So basically, we'd have to start building one nuclear power plant every day for the next several decades to get up to meet the energy needs, okay, from a non-CO2 producing source. So a lot of money, investments, new scale, even Bill Gates up at Microsoft is investing in nuclear companies. Okay, so I think eventually we'll probably see some build out in the nuclear community, but one of the big problems here is just simply siting these things. The process is so slow, okay, that it's hard to imagine, even if we accelerate this effort substantially, that nuclear is going to make a really significant contribution to the CO2 problem, but it is a viable, proven type of solution if you can move fast enough. Okay, probably the best option from at least technology point of view, okay, is to go totally solar. We have 100,000 times more solar power or solar energy hitting the Earth every year than what we need. Okay, so we're not resource limited. Okay, we're just technology limited. Okay, in terms of producing electricity directly from the sun. Okay, and then chemists like this option, okay, which is really to take the electrons from solar cells and simply use them to drive electrolysis of water. Okay, so we saw in the trivia questions, okay, there's a lot of energy in a glass of water. Okay, so if you have a few gallons of water, okay, and you convert it to hydrogen, say, with solar energy during the day, okay, you can produce plenty of hydrogen that you can react with oxygen, okay, to power your home. Okay, so instead of having 20 gallons of gasoline to push your car down the road, okay, you got to have a tank of water that was converted to hydrogen. Okay, you then burn that hydrogen, reproducing water, okay, and really, powering all your energy needs throughout the day. Okay, so water, you can think of as just a battery. Okay, it's a way to store energy, okay, convert it to hydrogen, okay, that we can then use as a fuel. Okay, so this is a very popular topic in chemistry right now, and actually our center is working on this, trying to make this process much more efficient. Okay, so in addition to the energy issue, there's all these things that we like to use every day, whether it's plastics or herbicides, or we all like to look good, okay, with the clothes we wear. Okay, we want pharmaceuticals. Well, we actually don't want pharmaceuticals, but if we need them, we like them to be there. Okay, but all these things come from oil, coal, natural gas. Okay, all these things turn to carbon dioxide. Okay, so in addition to using these feedstocks for energy uses, we're still bringing up a lot of oil and using it just to produce the goods that we're using. Okay, so if we're looking out a few decades, okay, and looking for a chemical solution to the energy problem, the feedstock problems, these materials types challenges, okay, what a chemist would probably tell you is that we can run the world, okay, if we can do appropriate chemistry by just extracting carbon dioxide from the atmosphere, okay, using some water to make hydrogen, okay, and then we pull nitrogen again out of the atmosphere. Okay, and if we can just do chemistry with these four molecules and then digging up a little bit of dirt, okay, we can actually produce the fuels that we need, okay, and produce all of the things that we have in our lives, okay, just by using these cheap sources without digging a lot of stuff out below the surface of the earth. Okay, so the way this is envisioned, we just extract CO2 from the atmosphere. We have H2 from water. Okay, with that, we can do chemistry just like a plant does chemistry to make organic molecules. So in principle, you could take CO2 and hydrogen to make all the pharmaceuticals, plastics, and herbicides, okay, that we need, okay, for our everyday lives. Okay, but reacting CO2 and hydrogen takes a lot of energy. Okay, so where are we going to get that energy? Okay, so again, from the sun. Okay, so if we have a really efficient way to capture the solar energy, okay, we can take that energy, we can drive these types of reactions. Okay, we don't have to pull a bunch of oil out of the ground to produce the things that we need. Okay, so water, again, really important part of this, or could be an important part. Okay, we take water, we drive it to hydrogen and oxygen. Okay, then we re-react it, create energy. That reaction can occur in a fuel cell. Okay, so during the day we use a solar cell to split water into H2 and O2. Okay, and then we run the reverse process at night where we bring in hydrogen, we bring in oxygen, it produces water and electricity. Okay, so again, with a tank of water at your house, during the day you're splitting it, storing the hydrogen. At night you're just running a hydrogen fuel cell, reconverting the hydrogen and oxygen to water. Okay, so you've got 20, 30 gallons of water. You can sit there and run your house all day long, okay, with some good solar cells. Okay, it's a pretty cool vision, right? I mean, if we can pull CO2 out of the atmosphere, I mean, we don't need that much water, to store a lot of that energy, and we have solar electricity. Maybe we should be in pretty good shape. Okay, so I think if you look at the chemistry community dedicated to energy, I mean, these are the big problems now that are being addressed in the community, and things that we're working on as well. Okay, so this sort of, if we think about the materials, chemistry perspective, we have all these plastics, pharmaceuticals, carbon-based materials, but if we look at most high technology, we look at the brains in our computer, we look at what's active, okay, in a solar cell. Okay, these things don't come from oil. These are inorganic materials that are derived from rocks. Okay, so these things, our feedstock is dirt. Okay, but surprisingly, there's limitations on even what you think would be common types of dirt. So we pointed out in the beginning here that it's astounding to me that in 20 years we could run up against an issue of even harvesting enough phosphorus, mining enough phosphorus for fertilizer. Okay, so even in this realm where we're thinking about these inorganic resources, we want to use them wisely. In making these devices, we want to make the processes very efficient, okay, in terms of the materials and reducing waste. Okay, so to do that, what we focus on, okay, is really looking at what we call the green elements in the periodic table. Okay, so these are the elements that are really plentiful. Okay, they're inexpensive, they're non-toxic. So what we try to do in our research is only look at these elements here in green. We stay away from the elements like thallium, lead, cadmium that are really toxic. Okay, and then these elements here are extremely expensive, things like gold and platinum. So we try to mimic what some of these elements do by using the cheaper elements. Okay, so we can make things on a grand scale, okay, and offer them at a cost point that's available to a significant part of the world population. Okay, so I think some of you are familiar with OSU. Have been sort of seeing this philosophy that's been developing at the university level, okay, around how OSU approaches its research. I mean, this has been an area that we've actually been thinking about for quite some time. And if you think from a strictly university research perspective, primarily what we're supposed to be doing is generating fundamental knowledge. So we're sort of out here in what we call the Bohr quadrant of science. Okay, so Niels Bohr gave us the model of the atom. I mean, he wasn't really looking for any type of practical application in any of that. Okay, it's really just trying to understand and describe nature. Okay, sort of at the other end of the spectrum, you have Edison, who's generating very little fundamental knowledge, but generating what's necessary to put inventions into use. Again, where we like to be with our research is sort of in this Pasteur quadrant, generating lots of fundamental knowledge, okay, while also doing things that all of us in this room might one day use. Okay, so Pasteur is a great chemist, okay, but he's also known as sort of the father of microbiology, taking all this good chemistry and microbiology and creating vaccines, pasteurization of milk, a lot of practical applications, okay, coming out of the fundamental knowledge side and going into use. Okay, so we try to really think about the basic science of what we're doing, but we're always pushing that to something that we can eventually to apply to a fairly large scale use. Okay, so the realm that we principally operate in is really taking inorganic materials, rocks, okay, turning them into thin films of these inorganic materials, because these types of thin films really drive essentially all of current high technology. Okay, so whether you're looking at your large area television, solar cells, integrated circuits, or very high efficiency low E windows, I mean, all of the function of those materials comes off very precise, very high quality inorganic thin films that have very specific electrical and optical properties. Okay, so what we're about is primarily working on these thin films, looking at high technology, looking at energy generation, okay, using chemistry to make these thin films. So what we're about is, again, doing simple chemistry, build what we call building blocks. And so we want to come up with a style of chemistry, something we can make very easily, okay, that can translate across a number of uses. Okay, so we do some simple chemistry in the laboratory, and we want to apply it to everything from really large area applications. Okay, so this is actually the size of the glass substrate that your television screen gets manufactured on, okay, over in Asia. Okay, it's about 3 meters on an edge. So it'll be a 42-inch television screen would get cut out of that piece of glass. Okay, so this is like doing electronics on a garage door. Okay, a really large area, and then we want to take this chemistry too and go into integrated circuit type applications where you're trying to make things as small as possible. Okay, and so here we're talking more molecular dimensions. Okay, but we'd like to do a single chemistry that can translate from really big, okay, all the way down to the tiniest possible devices that we can currently make. Okay, so the way that we do this is what's near and dear to Oregonians, and that's water. There's plenty of water here in Oregon. We like to use water for our base chemistries. It is the low energy solvent for chemistry. I mean, we don't have to process oil to get a solvent to do chemistry in. Okay, all we have to do is bring it up to the lab and purify it, use this ultra pure water. Okay, so what we do in the laboratory is really quite simple. I mean, very simple aqueous chemistries. So there's little molecules swimming around in this water solution. Okay, so we take those little molecules, okay, with an eyedropper, okay, we put them on to a substrate here. Okay, and our product here is in this yellow square. I mean, this is an inorganic thin film of aluminum and oxygen. Okay, this film has extremely special properties. Okay, the first thing you'll note is it's very homogeneous. Okay, so there's no pores or no cracks or anything in this film. Okay, and the surface of the film turns out to be atomically flat. Okay, so if you're walking along the surface of this film, occasionally you might see an atom that's out of place. Okay, so we've taken a little beaker of water here in an eyedropper, okay, and we've done something with water chemistry that would normally take you a machine that costs at least $500,000. Okay, but we're doing this on the benchtop, with a little bit of this water chemistry with students sitting over here in OSU laboratory. in the open and air, okay, nothing fancy. I mean, the only fancy thing here is the chemistry that we've done in that beaker. Okay, so we've basically made some of the world's highest quality thin films, okay, using really simple chemistries, okay, just using water. Okay, so we can do some amazing things with this. We can make films that are actually as thin as just a couple of atoms thick. Okay, again, we just do this on the bench top, okay, out in the air. Okay, we can stack these films into really complex patterns, which has a lot of implications for a whole variety of different electronic and energy devices. Okay, and then what we can also do is take the film or the materials that we have up here in the solution, and we can make them very sensitive to light. Okay, so with that sensitivity to light, we can actually draw the world's smallest features of inorganic materials directly, okay, onto different types of substrates. And this is very important to companies like Intel and Samsung that want to make your computers and smartphones a lot more powerful, faster, okay, as well as consuming much less energy. Okay, so we've taken this really simple water chemistry and the first time ever shown that you can take solutions and make these extremely high quality inorganic films for electronics and energy production. Okay, so the concept here then is that we have water sitting in a solution that's going to convert it into a solid. So that just looks like an ink. Okay, so now what you can imagine is that we could take something like a printing press. Okay, we have water and an ink. So now we can start thinking about shooting, okay, these inks, okay, down onto a press and actually printing electronics. Okay, so there's lots of research now going on, some development efforts, trying to make this happen so that we have printable electronics on flexible type substrates. Okay, another thing that actually just happened this year, there's a company in Europe called Bennick. It's got a big machine here that takes glass off a window glass line. And they're now taking solutions, okay, like we're making, and they're just shooting it onto that glass and making the conductive layers necessary for low E energy windows, okay, just directly, okay, on the glass line. Okay, so they're claiming about a 90% cost reduction in the manufacture of these low E windows. And actually, if you look at the market penetration of low E windows, throughout the world, it's actually quite low. Okay, so with this process driving costs down so much, I think over the next few years we'll see much larger use of low E windows, particularly in the developing world. Okay, the nice thing about this is that this company now is allowing us to use one of these machines here in Corvallis. So we're actually the first world site where they'll have a laboratory scale machine for putting down these solution-based films for research and development purposes. Okay, so I thought I'd put in just one slide on real chemistry here to give those chemists in the audience some view of what we're actually doing, which is, again, quite simple. So we do things like take aluminum nitrate, which is quite soluble in water. Okay, we can add a metal such as zinc to this. What that zinc does is cause all of the aluminum atoms to come together, okay, into what we call these nanoclusters. Okay, and that nanocluster is actually just a small fragment of the actual solid film that we're making. Okay, but in this condition, this cluster is quite reactive, so that when we put this material onto a substrate, okay, we can heat a little bit, okay, and convert it to a film such as aluminum oxide. So the critical thing here is, we want to get some structure building, some cluster formation. We want it to stay fairly small so it stays fairly reactive. We don't want these clusters to get too big so that they become unreactive, and we have to put a lot of energy, okay, into the system to get it into this high quality film format. Okay, so if you think about the overall process here, we get a zinc byproduct, okay, but we can recover that byproduct, okay, and use the zinc again. Okay, we get a little bit of nitrogen oxides off this, but in principle you could capture those nitrogen oxides, reuse them. So really this is essentially a zero waste process, okay, because everything we produce here we can actually use or reuse, okay, so there is no waste associated with producing materials from this type of aqueous process. Okay, so we use these small clusters then to make these thin films. We apply them across a whole range of different possible applications. So here's an example where we took and created a new platform for looking at taking sunshine and converting it into hydrogen, oxygen, splitting water. So we took a really thin film of nickel oxide where we can actually count the nickel atoms one by one, and we can look at the efficiency of converting water to hydrogen and oxygen, okay, getting rid of a lot of problems with trying to do these measurements in this really thin film region. And what at least what Shannon Betcher showed in our center is that if you take a little bit of nickel, add iron, you actually get the most efficient catalyst that's ever been found for splitting water. Okay, so there's decades of research been done around this iridium oxide material, which is extremely expensive. And that was always thought to be the most efficient catalyst, but by moving to this thin film platform, okay, we've actually shown that inexpensive nickel with a little bit of iron, okay, is actually the most efficient catalyst now known for splitting water into hydrogen and oxygen using electricity. Okay, another area where we've been very successful is to make the film sensitive to light. Okay, and what this allows us to do is to create a pattern of light through a very short wavelength, what we call extreme UV generation. This experiment was actually done in Switzerland, where they can mix this light and create a very, very fine pattern. So what we've been able to do is basically draw these lines of inorganic material here, these white lines. Okay, they're about 8 nanometers wide. So for us, that's about 40 atoms. So we got lines that are 8 nanometers wide, spacing of 8 nanometers. Okay, that's the highest resolution pattern that's ever been written, okay, using light. Okay, as a company like Intel, okay, look at this as a promising technology for keeping them in business for a few more decades. I mean, if we can show that this is a sensitive, reproducible process at these levels, and companies like Intel will be around for decades, and your smartphones and PCs will continue their advancement in terms of their processing speed and, you know, also driving to much lower power usage. Okay, so we're doing all this cool science, you know, making tremendous breakthroughs, okay, but we want everybody in this room to be able to use this. So we want to get things out of the university. Okay, so in these centers, we're also trying to do that. Okay, and our process is really to train the students to do that. Okay, so we've collaborated with the National Collegiate Inventors and Innovators Alliance to sponsor a series of workshops available to all the students in our center. So they come to Corvallis about 4 times a year. They're working with the students on a continuous basis, you know, training them to be what we call innovators. Scientists, by and large, don't want to be entrepreneurs. Entrepreneurs tend to focus on the business side of translating innovations. I mean, most science students still want to get in the lab. They want to innovate. They want to have scientific breakthroughs. Okay, but if we want to translate the science, they have to be able to talk to the business community, and they have to be able to recognize in their own science whether or not anybody's actually outside of science ever going to be interested in it. So we try to expose them to the business community. We train them to speak the language of the business community. okay, so that we can get some of the science that we're doing out into use. Okay, so Corvallis is just a great place to do this. We have a unique infrastructure at OSU, okay, as well as in the Mid-Valley area here. So specifically at OSU, the OCCD, has been very active in building up the programs available, to get our findings out into the real world. So I've probably been reading in the papers about the accelerator program that's coming online. Okay, and lots of activity in OCCD helping with this effort. There's also now the OSU Venture Fund, okay, that allows students to come in, after they're graduating. I mean, we've trained them on how to do all this. Okay, they have great ideas, but they have to build something, some basic engineering or science, okay, into an actual company. I mean, they need some funding to do that, to keep their ideas moving. Okay, so at least here at OSU, we have the OSU Venture Fund available, okay, to keep these students funded for a period of time so that they can continue to demonstrate, okay, that their projects actually have real world potential. Okay, then beyond that, over on the HP campus, we have the Oregon Nanoscience and Microtechnologies Institute. They have a GAP fund, okay, that allows, again, this group of students to stay in business, giving them a long enough runway to get them to the point when they can get some investments that will keep them around for the sufficient time that they can get their technologies actually out into use. Okay, so we've been going through this process now for a couple of years here in town. We've had a number of successes already. Okay, so over near the university, there's a startup called Imperialio that came out of our center. They're really focused on green manufacturing, particularly in the semiconductor industry. Okay, so you saw in the trivia questions that there's 1,000 grams of waste, okay, for every gram of an IC that's produced. So this is a company really focused on these chemistries that we've talked about that are very atom efficient. They're able to cut steps out of the manufacturing process to save on waste. Okay, but in this process, you just can't walk in with an environmentally benign process. You have to come in with better performance, better ultimate device performance, as opposed to just saving energy or saving materials. So that's what Imperialio is also about, is moving to the next level of performance. So they've taken our water-based chemistries. They're in development lines now at places like Intel and Samsung. Okay, one of the things they've been able to do is use the patterning technologies, okay, with this EUV technology. So this is the source of light that's being used to make it's being developed to make the next generation patterns. So the new fab up at Intel, they're installing these things. They go for about $100 million a machine. And when this company, SML, wants to show what the capabilities of these machines are in terms of the resolution, they come to Imperialio, okay, and they buy the material to show how well their machine is actually functioning. Okay, so you've got 12 people here in Corvallis that are contributing to the highest resolution, smallest structures that can now be patterned, okay, with this next generation lithography machine. Okay, so the same company has worked with LG Display. So this is a 17-inch display that was manufactured using only water-based chemistries, okay, to build transistors. Okay, so in our OSU labs, we make about 25 transistors at a time. Okay, so Imperialio took some of that chemistry technology out to LG Display and took our 25 transistors and showed that at least it could be scaled to 2 million transistors. Okay, and you could actually drive an okay looking display using only water-based chemistries. Okay, in addition to Imperialio, we also have another company here in Corvallis called Morphix. Okay, and again, they're basing their technologies again on the really high quality thin films that we can make using some of the processing that we have available. Okay, and the idea here for this company is that we have a couple of metals. Okay, in the middle we have this really high quality insulating material. Okay, and what we can do with these really smooth metals is get electrons to actually tunnel from one metal to the other metal. That tunneling effectively occurs instantaneously. Okay, so one of the interests here is potentially in high-speed electronics. Okay, but first generation is just to use this simple device as an on-off switch. Because what we can do is put a voltage between these metals and a high enough voltage, then we get a current on. And then we can back that off and turn the current off, so we can just switch back and forth. Okay, and that's the basic switch that you need in a display. Okay, but manufacturing this type of switch only takes 3 layers, takes 1 or 2 steps. The transistors that are in all our smartphone displays or PC displays take about 6 or 7 steps. Okay, so the idea with this technology is that we can readily take it into current fabrication plants, can go from 6 or 7 steps down to 1 or 2 steps. Okay, all of a sudden that $5 billion plant now becomes worth 3 times more because it can produce at 3 times the rate, okay, as what it was doing before, the introduction of this particular switch. Okay, there's all kinds of other applications, potentials associated with this simple technology. And again, we have a company right here in Corvallis, okay, that's trying to make this a reality. And hopefully, a few years down the road, everybody could potentially be using this in your display applications. Okay, so I'm going to end this evening, with a brief consideration again of what the real challenge is around solar energy. How we might think about using some of this chemistry to very rapidly address the solar issue and how we can make this a really significant part of the energy use here in the world. Okay, so if we wanted to, really make a significant dent, okay, in the nation's energy use through solar energy, okay, we'd like to generate about 3 terawatts of power. Okay, to do that at really modest efficiency, okay, we would need to cover this amount of area of the United States. That's actually not so crazy to think about that. It's getting pretty close to the amount of area that we've covered with the interstate highway system and our roads. Okay, so, that's the amount of area that we need. So this was proposed by Nate Lewis a few years ago. I don't think he quite realized how forward-looking he may be in placing it in that part of the country. Because I was actually raised right there, and I went to school in my undergraduate days right on the edge of that square. Okay, so that's the Dust Bowl area. That area right now is agriculturally quite rich area. So if you thought about putting that area under solar cells right now, you'd probably have a lot of folks upset. Okay, but that area survives because they're pumping water out of the Ogallala aquifer. Eventually they're going to take all that water out. Okay, when they do that, this is going to be a great area to harvest electrons from the sun rather than harvesting wheat. So, that's actually, could be a boon to that part of the country, okay, if we had a cost-effective solar technology to begin to cover that area. Okay, so, the solar challenge is really coming up with cost-effective solar generators. Okay, but the real issue comes down to making that extremely efficient, because the real problem in solar is all this area and defining the real estate to put those solar cells on. Every piece of real estate, I don't care where it is expensive. Nobody wants to give you low-cost land. They don't want to give you a low-cost roof. They don't want to give you low-cost anything. Okay, so ultimately we need really, really low-cost technologies, okay, and then we have to deal with the real estate, the installation issues, okay, which are probably more, going to dominate the cost of solar. Okay, so we're approaching this from a technology side. We sort of have these water-based chemistries that we view as a way to make things really fast. Okay, but in the solar area, we're also sort of materials limited in terms of scaling to these really large areas. We really only have one option right now for scaling, and that's silicon. So we have a big silicon plant, Solar World, up in Portland, that's making 6 or 8 inch round pieces of silicon. You saw that area that we put up here. I mean, it's hard for me to imagine that we're going to cover that area 6 or 8 inches at a time. I mean, we need some new technologies that we can roll out on a printing press, okay, to cover these enormous areas, okay, in a fairly short period of time. And if we're looking at the global climate change curve, okay, we'd like to find some technologies that we can sweep into place, okay, on this, this technology curve that gives us, sort of an exponential introduction. Okay, so what we need are new materials. But if we take a conventional view of identifying making new materials, okay, what we tend to do is make a material, okay, then we look at all its properties, and if we're developing these for solar, what we do after several years is just find out the material, has some failure mechanism, okay, that makes it impractical to put that material into solar. Okay, so what we're trying to do is take an opposite approach. Okay, take a computational search approach, okay, where we actually define the properties that we need from an electrical optical perspective. Okay, use those computational capabilities then to do materials by design and basically, go in a reverse process compared to what we do traditionally. So it's kind of like playing Jeopardy. We have some answers, and then we look for the questions around the types of materials that we want to make. Okay, so what we do in this process then, we work with computational physicists who can do hundreds or thousands of calculations on the world's most powerful supercomputers. We'll take a few results of that, do some experiments. Okay, we feed some of the results from the experiments back, okay, into the calculations to refine the procedures, the models that we have here. So we'll iterate this loop a few times, okay, and then we drop out what we think is an optimized target function. Okay, so this could be some specific electrical optical property in a solar material. Okay, we do all this under the framework of doing things with the green periodic table. And if we put all this together, what we can start doing is just knocking out new opportunities from a materials perspective, okay, in terms of designing solar materials, okay, using this really high-speed inverse design approach. Okay, so with this, we have now identified, okay, a number of new materials that were never even thought of previously, okay, that can lead to really high solar absorption, materials that have good electrical properties, okay, and are built from readily available earth-abundant elements. So we discovered this nice, simple material here based on iron, silicon, and sulfur, the 3 cheapest, most abundant elements in the Earth's crust. Okay, we have a whole variety of other materials here that have fantastic optical properties, compared to what's currently in use. Okay, so we're sitting here turning the crank as fast as we can, okay, with this computational experimental approach, okay, finding lots of new materials. We're actually patenting these materials at OSU, okay, so that we can have a base for, again, translating this out so that we can have some new opportunities to scale solar really fast, okay, really big, okay, relative to what we have currently available. So we can take these things, we can then take our water-based chemistries, okay, and start building up, the types of materials that we need, to really realize things at more of a terawatt level, trillions of watts, okay, instead of current capabilities, okay, which are billions of watts, and will take us a century, okay, to get up to this terawatt level. Okay, so what we're trying to do then, okay, is really, new chemistries, get on this technology curve, okay, train students so that they can translate, okay, what we're doing on the basic science level, okay, into use, and hopefully make this happen really fast so that we can contribute, make some contribution to climate change. Okay, so I think we can sort of start envisioning a future, okay, where there are solutions that are cost effective, okay, in dealing with our problems with fossil fuels. So with that, I think I'll go ahead and end, and happy to answer any questions.